Hello, hi. I'm Nicholas with Mabru Power Systems. Today I want to go over two parts in this video. First, we're going to be talking about, this is our 12,000 BTU, 115 volts self-contained unit. And I want to compare that with our 12,000 BTU 12 volt unit over here, because I've had a lot of questions as far as why I would go with a 12 volt system when I can just get a 110 volt, run it through an inverter, and seemingly get the same type of use. And that is a very common misconception, and we do have some very big differences. I'll go over it, but I'll show you as well. This 12,000 here will draw somewhere around 40 amps when it's running at full speed, full blower, pump running. Everything will be at 40 amps, could go up to 42. This unit here, 12,000 BTU, 115 volts. By the time I go through an inverter, even an inverter as good as this one here, I mean, we're using the Magnum 2800. It's a bit marginal to get the unit started, but it does get the job done. And we're talking about a consumption right around 100 amps with this unit running with the pump and everything. Already our 12,000 BTU 115 volt is one of the more efficient systems in the market available in line voltage. But the differences on the 110 volt versus the 12 volts are just night and day. So I also wanted to go over as well the lithium systems. There seems to be another misconception. Lithiums have to be really complicated. There is a bit of a higher expense, but at the end of the day, when you compare everything, it is really actually more economical to go, and it's the best way to go. So I'm going to grab the camera over here, and we're just going to slowly go over the different systems. So for example, this inverter is set to charge lithium batteries. So this inverter is charging this battery directly. This battery here, which is where I have the 12 volt unit hooked up to, is being charged by this device here. This device here is a DC to DC charger by Sterling Power. This is a 60 amp version. So the idea is, or the way we're doing this is, I have this battery charger. It's a quick SBC 700, so it's also a 60 amp battery charger. I have this battery charger set to AGM, which is charging this battery over here. This Optima D27M is, once this is charged, this will sense that the voltage has gone up. I believe it's 13.3 volts. Once it goes over that, this will kick in and begin charging this battery here. And so it'll charge at any point that this battery is being charged. So whether I'm going through an alternator, whether I'm going through a battery charger, this will take over. Or I'm sorry, this will take over. So it replaces what would be a VSR, charge relay, however we want to name the device. But instead of combining the two batteries, it's taking power from one battery, putting it in the other battery, and once again, this will not discharge this battery. So I'm going to cut off my power. So if we look over here, see that I'm inverting. I'm going to now turn this unit on. So this is the unit. This is the 12,000 BTU 115 volt, which with the fan at minimum, I'm still drawing a little over 10 amps, 11 amps. And then once the unit kicks on, I'm just going to increase the fan speed. So you saw the fault, we got close to the limit there, but we did get the unit running. Starting off here, we're starting at 76 amps. I'll let it run for a little bit, and while that that's happening, I'm going to go and get the 12,000 DC going. So you saw the amperage spike when the unit came on. I saw it jump past 200 amps. Have to go back to the video and see where we were really at. This is the standard display that comes with the units. It's a monochrome touchscreen. Oh, I'm actually not at full speed, so let's do this correctly. I just want to show, and I'll slow it down again. But we're already at 90 amps, 88, 90 amps. Hopefully you can hear me a little bit better. This is our touchscreen display, color touch. So I'm going to now turn this unit on. And then that one. If we look over here, battery voltage, amperage, so fan just went to full speed, and then just to show that we're not going to have a voltage, an amperage spike, it's going to slowly increase. We'll let this one continuously climb. This is once again full compressor speed. Let's actually confirm that. Yeah. So we're asking for 60 degrees, and it's 77 in here now. The unit is extremely quiet. You can barely hear the compressor running. So I'm right now at 31.6 on the 12,000 DC unit, so 31.6 amps at 12.9 volts. And then on the 12,115 through the inverter, I'm currently at 93 amps at 12.7 volts. So it's a pretty substantial difference when we're considering the cost of batteries. I would need to at least triple the bank size to be able to maintain the same size unit running, just based on the amperage differences. Okay, so looking back again, this unit is set to the possible lowest fan speed. This is the 12,115, and I'm still drawing 90. Over 90 amps. We have the 12,000 DC. Seems to have settled itself high 25s. It will go a little bit lower if I leave it running a bit longer, but I mean, medium speed I'm down to 25 amps. And then what I'm gonna do is I'm going to fully slow it down. So now when it reaches set point, it's just going to go to the lowest possible speed. So now I'm reading my return temperature and my discharge temperature. And so at the lowest speed, I'm still pushing a differential of 14 degrees. And that's a little bit about the 12 volt system, the direct comparison of the two units. They both have copper fin evaporators. They both have the B30 condensing coils, stainless steel chassis. So this is a 20-year rated coil. Copper fin we've gone over before, but once again, it's just to remember that we have copper on copper, so we have better heat transfer. We have the antimicrobial properties of the copper, as well as the added longevity due to not having the similar metals. It's copper on copper, instead of having copper on aluminum as all the other manufacturers are doing. I hope you enjoyed the video.